Welcome back to our X-ray astronomy hands-on and to our Nation Science Day X-ray astronomy hands-on. And Vishal, Gaur, and Pinaki Roy are also with us, PhD students working with Aru Berry. Aru has also joined us. So I'll add everyone into the stream, and you can see in the screen share there is the Google Colab. Vishal Gaur has shared, and I think I'll Aru or Chetna, was there anything you wanted to point out to the student before we hand over to Vishal?
Sure. So, quick instructions as we have always keeping giving these instructions several times. So, please open your Google Colab document or also the shared Google Doc which was shared in the group, so that you can also type in the same commands and be on the same page when these tutors are going to demonstrate the program as we move along, and play along with this light curves which was shared yesterday. I hope you all have downloaded the light curves. If you have, then please those light curves will be fetched from the Google Drive directly in these programs via Google Colab, which we are going to play with. So keep all your tools ready. And if you are also having any delay or any problems, do let us know. There is no hurry and there is no rush. So we will be keeping up pace. But try to be together, and wherever you get stuck, do post your comments on the chat box so that we understand where you are stuck and what is the problem, so that we try to figure that out. So like as I mentioned earlier also, it is good if you can create the plots as we move along these exercises. That will also give you a confidence about doing real data analysis with the real data, and which you can take up later on in the more advanced workshops, which might follow up based upon your responses and interest in the subject. So I would suggest please give us those PDF or share those PDF files also at the end of the workshop, that you can do via WhatsApp group. So now I will hand over to Vishal, and Vishal will proceed with the programming with Python and working with those data. Thanks, Vishal. And are you around?
Yes, ma'am. Hello, everyone. So let's start with a Google Colab hands-on session. So first, I will like to show you, if you haven't done if you haven't add the data to the Google Colab or a Google Drive. So what you can do is you can add the Google data to the Google Colab notebook temporarily. So when you will be terminating the session, this data will just vanish. So this is temporary kind of thing. So you can upload your all the data files here and just work with them with the session. So in the first block, we are importing all the packages we'll need for the workshop. So first one is NumPy, matplotlib, which is used for plotting purpose. Then AstroPy, and it's the main package we'll be using to analyze our fits data. Then we are importing this warning. This is just this is how you import your Google Drive in your Google Colab notebook, and you mount that Google Drive at some path. So when we run this block, it will authorize your Google Drive. So you need to go to this link and sign up with your account so that you can access the data. You can copy this authorization code in here and enter. So now your Google Colab authorized your Google Drive, and you can use all the data which is present in your Google Drive. And the path of your Google Drive is this. So I hope you have already know how to open the data, but if not, then this is how we open our FITS notebook, FITS data using the AstroPy package. So AstroPy has this function known as import FITS. So using this, you can import the data, FITS data. So let me just run this block. Yeah. So first one, I'll be showing you the data from a pulsar, which is 4 binary, X-ray binary, which is 4U1626. So when I run this block, first thing it shows me the info. So it's the basic primary table which info which we are getting from this FITS file. So first extension is primary, which only contains the header. Second one is rate, which contains all our data which we'll be using, the time series, time versus rate. So this is how we are importing the time column in our as a numpy array, and this is data which is just the rate count per second. So the exposure of this data file is 159 seconds. That means this is 159 seconds worth of data. And the time resolution is 0.125 seconds. So time resolution is basically you are getting uh, you are getting a particular count per second in 0.125 seconds. So you can if the time period is less than 0.125 of the binary, then you can't able to like detect it. We'll talk about this further, but this is what a fits file looks like. So how I know that this is the rate column, the column name is rate. So for that we can use the fv software. So I hope you have installed the fv fits viewer in your laptops. So you can open your fits file, the fits file which I was using in this. So you can open the fits file and view it in fits viewer. So from here you can plot, see all the tables which this fits file have. So you can see the first column name was time, the second was rate. So that's how I know the column name is rate, and I opened it in Python.
In case someone is not installed and just working only on collab also, it's okay, right?
Yeah, it's all
You
okay,
can
but
manage.
you have to know the column name, this rate. So for that only I'm using fv. So there is no need to like, if you don't have fv, then also you can open the fits file. And usually in case of fits file, the column name is usually rate or counts. So you don't have to like use fv every time. So it's okay. So the first column which I got is time, and the
So,
second is
one second, Vishal.
yeah.
So here also, when he has used the Python script and said HTU info, so it has also given you the rate information. So
Yeah.
the information about the column can also be obtained from this. So there is no necessity to open FV. Things can be done in
No, the
Python.
rate here is the extension name, not the column name.
But
So under this extension, the column name can be different.
but the this information they can obtain in Python also. So
Yeah,
there is
you
no all that
yeah, yeah,
information you can dump your data with the all the columns and the extension using the Python as well, which is not
yeah.
done here. Hmm.
So I just wanted to show you the FV because it's more of like a GUI, so you can like, see that. So I got the time data and the counts per second, which is stored in the data. So let's plot it. And this counts per second versus time series is known as light curves. So let me just show you the plot. So this is counts per second versus time plot. Let's look at the Python code. So it's just the standard plt dot plot. So this is how we are plotting the data in Python. So the first argument is time, which should be on the x-axis. The second is data, which is on the y-axis. And this is adding title, x label, y label. X ticks are these ticks which you need in the plot. So you can define this like how many ticks you need in the x-axis. And numpy.linspace is just gives you an array, and the arguments are the like starting point, the ending point, and how many ticks you want in the plot. Then this plt.grid gives you grid, and plt.xlimit by using this you can set from how much to how much you want to see in the light curve, like from starting range and the ending range of the light curve. So if you are doing this exercise right now, only thing you need is plt.plot. So it will show you the this count per second versus time plot. So I'll prefer if you are doing this with me. So this will be more like of interactive section, and you can post your doubts right now. So this is the light curve which we use. So this is a very important aspect of your starting data of data analysis, because this light curve shows you can give you hint about the source very much. So using this light curve, you can see if there is any thing which should not be here. We'll talk about this more using the different light curve.
So, okay. So one thing which I wanted to add to Vishal's point. So, Vishal, if you can move up to the time resolution segment of the. So here Vishal was talking about time resolution, which is given here as in terms of seconds, 0.125 seconds. So this is the light curve which we have provided you, and this light curve is something which is kind of a product which we have already given you as such. But these data are reduced from the raw data which we obtain from X-ray observatories. So if you remember in the talk, I mentioned about a few observatories like NICER, AstroSat, NewStar. So every detector has their own reduction pipeline, and using those pipelines and writing your own scripts, you reduce the data and get a usable format of data or products, which we call as in terms of light curve. So, which is intensity versus your time information recorded in arrays. So, this is the light curve which was extracted with a time resolution of 0.125 seconds. So, when Vishal mentioned that you cannot have a data you cannot plot this light curve with a time which is less than 0.125 seconds, means that I have used this 0.125 seconds as a time resolution for extraction of the data from the observatory or the raw data. So I cannot go below this value, but that doesn't mean you cannot plot the light curve above this value. So 0.125 is the minimum time resolution of this particular light curve. But now, based upon the observatory from which observatory you have extracted data from, you can have different time resolutions based upon the sensitivity of that observatory. So, but for the given exercise, you will be playing with the slide curve, which has a minimum time resolution of 0.125 seconds. So, I think Vishal, are you
Yes,
plotting this slide
Um,
curve with the default resolution of 0.125
yes,
seconds?
yes. Right now,
so
Okay.
I'm
Vishal,
I want to add something here, meaning there is something called bin time and there is something called rebinning. So every satellite, for example, the satellite is recording data at say 1 microsecond. Suppose we know that we want to study the variability of say 1 hour. So instead of reducing the data at 1 microsecond, we reduce the data at a higher bin size. So here Vishal has reduced the data at 0.125 seconds. And now you can rebin this number later on depending on what kind of variability you want to study. So there are two things. There is one inherent binning of the detector. There is one binning by the astronomer depending on his requirement, and then you can anytime rebin at any number greater than 125 milliseconds.
Vishal, somewhere
yes.
in earlier context, there was a question from Jishant asking how can you type them side by side, and I don't know whether the later discussion clarified it for him. Jishant, you could maybe ask a little more clearly, or
Uh,
did you get the context, Vishal? Then you please go ahead.
No,
so
I
I
didn't
think
get. Yes,
so,
yes, yes.
Vishal, so basically, we should allow them to give some time to them to type in, because we are moving a bit fast, as I understand from Jishant's point, that they need some time to type. So
Okay.
keep your, commands open for few minutes, so that they are, and from the chat box, ask them orally, so that they
Uh,
can respond to that whether they have finished typing the commands. So then only they will be able to do hands on side by side. Okay, so
I'm
we.
also yeah. Yeah. And one more question is there from Gauri Patti, who is saying that files that you had sent were of some other extension.
Yeah,
uh,
so fits don't doesn't mean key you have the extension dot fits. So it can be dot lc dot lcurv. The extension name doesn't matter. It's the file type which matters. So the file type is fits. So it contains the tables and everything. That doesn't mean you have the fits extension like dot fits.
So, if I remember correctly, the same light curves which she is showing here is been shared by you. Only one data file, which is pulsar.fits, is a different with different extension. But as Vishal mentioned,
Yes.
that extension does not matter here. It is more like what how the data are recorded, and data is recorded in the FITS format, which is .fits or it can be .nc. And with your Python program, you can open any type of FITS file, and this is what we are doing here with the FITS open. So, now question to everyone: has everyone imported all the libraries, which was the first segment of the program? Vishal, can you move on to the first
Yes.
segment of the importing libraries? Please respond to us over the chat box so that we are on the same page and we understand that you have imported all the libraries, because these might not be the same libraries which you have been using for working with the ASCII data. So there are some additional files or additional libraries which are required for playing with the FITS version of the file. And as in the previous coding camp, also there was a demonstration or why do we need FITS format because of handling of huge data. So usually astronomy or rather X-ray data comes in the FITS format. So that's why we wanted you to play with that and using Python. So please make sure that everyone has imported those libraries, which is the first part of the program.
So if anyone is having any trouble, put it in the chat. I'm going to track the chat, and you all look at the window what is being discussed. I'll take care of the chat and alert
There,
you if somebody needs something. I'll alert you.
Okay, so Gauri has mentioned that AstroPy time series part is showing an error.
no, that
So,
is because time series you should write capital T and capital S when you import time series. So that will give an error. Same goes for line at line number 3. Import time with a capital T.
Yes. These functions are case sensitive, so you
Case
have to.
sensitive, so be
Yes.
very careful.
Yeah.
Okay, go ahead, Vishal. Thank you.
Yeah. So when you're doing all this, writing the commands, I don't want you to write whole command, like all the commands for like plotting. Only plt.plot will work. So right now you can just plot the time versus count per second. You don't need to give the title, X label, Y label, etc. So, and please let me know over the chat WhatsApp if you want me to stop somewhere, like go to a particular segment. So let's move further. So as previously mentioned, we can again rebin the light curves. So the default resolution was 0.125 seconds, but let's say we want to see a feature which is like a 10-second periodicity in the light curve. So we want to like zoom in, or you can say we want to reduce the data points. We want to decrease the resolution, increase the resolution. We want to uh, let's say we want a new bin time, like new resolution, to be 2 seconds. So we want in 2 seconds, we just want one data point. We don't want many data points in 2 seconds, so that we can like see more clearly what's happening in the light curve over the longer times. So what we can do is we can set the Dubin time as 2. So here you can set the give the Dubin time which you want. So we do this bins is equals to numpy dot arrange. So this numpy dot arrange does this. So you have to give the initial, like the first point, the last point of the time series, and the new bin time. So it creates the uniform array between these two numbers, time, zeroth element of time and last element of time, and divides these two in number of this new bins. So it will create first point as time 0, then the next point would be time zeroth element of time plus new bin, then the third element will be time zeroth element of time plus 2 times new bin. So this will create a uniform time series. Then you have this digitized this you can like this is beyond the scope of this answer session, so I won't explain how this numpy digitize work. But basically after this digitize and this uh, command, what you get is the number of bins. So basically 2 second worth of data will be combined into one data point. So you'll get a time data point and the count per second data point for 2 seconds. And when you plot this light curve, which was binned for 2 seconds, and you run this plot. Yeah. So I'll do first one this. Yes. So you get this light curve. So now you can see it's like we in for 2 seconds we are getting one data point, and we can clearly see these peaks if in this light curve, which was not much visible in this light curve. So what we have done is we have combined 2 second worth of data points in just 2 seconds of data in one point, and we again plotting the light curve with the same commands. So I'll just stop for at this point so you can type in.
So, as an exercise, you can play with this number, Newbin number. You can use any number which is above 0.125 and see how your light curves look like. I mean, there will be a effect of the rebinning factor every time. So, as Vishal mentioned already, that it's basically you are averaging out for 2 seconds. So if your detector has a time resolution of your say microseconds, but we extracted light curve with 0.125 seconds, which means we have collected data for every 0.125 seconds in a light curve. But now when you are rebinning it with further 2 seconds, which means now you are collecting data over 2 second segments each, and then it's kind of a smearing out of your data. And when you average out large number of bins together, the features becomes more apparent at times, more like variability, which Chetna also discussed in her talk, that you have some kind of random variability in the light curves observed in X-rays. So those variability sometimes becomes more apparent, and there are also effect of binning. So at different binnings, so if you compare this with the previous light curve, which was with the default resolution of 0.125 seconds, there you were not being able to make up more features in the light curve. But as you increase the new bin number, the features become more apparent. So this is the effect of binning the light curve or rebinning the light curve. So please do this exercise, and you feel free to use a different number in your reports when you want to submit.
And since you are typing this code, I want to mention two things. First one is like Newbin number, the number, this number, you cannot go beyond the time resolution of the default time resolution of your satellite. Like if the data was originally reduced as 0.125 seconds, you cannot Newbin this time series into like, let's say 0.01 seconds. And also you cannot go beyond the exposure time. So if you go beyond the exposure time, it doesn't make any sense. Like if the this was I guess 150, yes, 159 seconds worth of data, so you cannot set your new bin time to, let's say, 200 seconds. So anyway, the what it will do is it will combine all the data from the plot and give you one single point. So the new bin time should be in between the time resolution and your exposure time.
Yes, very important point.
Yes, and the second thing is, if you want to probe into the light curve and you want to, let's say, detect a periodicity of, let's say, 1 second, and you are binning the your data in 2 seconds, so your 2 seconds worth of data will be combined into one data point, but the periodicity was of 1 second. So you'll have to see what new bin number you want to set, because you don't want to lose the periodicity or that feature in the light curve. So the new bin number value with value of new bin depends on what type of feature and you want to extract. And the biggest advantage of doing this is, let's say I had 10,000 data points, for example, and the actual number is much more than 10,000. So you have 10,000 data points. Now you have to work with those 10,000 data points, but the time resolution was 1 second, and the periodicity, let's say, was 100 seconds. So you don't have to process the 10,000 data points. You can bin the light curve in, let's say, 10 seconds, so that your number of data points will be reduced by a factor of 10. So then after that you will be having 1,000 data points, and you just have to work with 1,000 data points. So it's a biggest advantage of reducing the data kind of. So I hope by now you have typed all these commands, and then again you'll have to do plt.plot this time bin and data bin, and you'll get this light curve. So as you can see the curve, you can clearly see these features. So let's
If any,
look
if
at
any,
the
wait, if anyone is stuck in the previous segment, please let us know over chat.
yes. So what third thing we can do with this light curve is we are seeing this light curve in the time domain. What I mean by this is we are seeing this light curve as counts, number of counts per seconds we are getting at a particular time. So, so we want to detect the periodicities in this light curve. That means we want to see if there is some pattern in this light curve. So to detect these, the there is a very nice tool known as Fourier transformation, and I hope you guys have just seen the theory and go through once. So Fourier transformation is just going from this time series, time domain, to the Fourier domain, basically frequency space. So it is the plot power versus frequency is known as power density spectrum. So we use this fast Fourier algorithm. So it's kind of Fourier transformation. It's just it's faster than normal Fourier transformation which we do. So you can read about fast Fourier transformation. And for the hands-on session, we are using the FFT function of this NumPy package. So we are taking the fast Fourier transformation of our data, and we are calculating the power. So power is FFT. This function gives you the in power in complex number. So we take the absolute value of the complex number and get the power. So then we define our frequency space. So since this is power versus frequency, so we'll have to convert our time series to the frequency space. So this delta t is basically the time resolution of the data, and this is how we define our frequency. So this is k, which is an integer going from 1 to n is the length of the data, divided by n into time resolution. So this f1 is basically giving you the frequencies from the time domain. So we then I don't need this. So we then need to plot this frequency versus power, and let's run this. I'll come again with to the code. So this is what it looks like. Yes.
Vishal, you are going to go through this again, right?
Yes.
While
Yes.
you are
Code.
going through this, could you also do second and third code cell just once more? Because
Yeah,
Second and
Vishal
third.
has said
Sure.
that he has not caught up with that, and I would suggest to
Sure.
all of you, maybe time to time take quick screen captures and save them on the side so that like you
Yeah,
can
that will help
catch
actually.
up.
Yes.
Okay,
and
go
another,
ahead, Vishal.
Vishal, you can pause for a few minutes for them to come on the same
Yes.
page.
I'll.
Don't move on
Yes.
immediately to the
Hmm.
next.
No,
So
yeah,
give
you
them,
could show.
yeah, keep a time record. Give them 5 minutes to copy the commands. Otherwise, if we are demonstrating everything, it might rush.
Hmm. The
So wait
second
for.
and third code cell as
Hmm.
well. Yeah.
Second binning, right? Second one is yes.
Yeah, because typing will take them some time, and they are not familiar with the Python. Not everyone will be familiar with this kind of coding. So please wait for some
Yes.
second. So this part
So
will be allowing you to rebin the data. So please
yes.
follow these commands. 2 minutes here.
Oh, oh, I was, yeah. You're going to the third one now. I was
Yes.
just saying that we have very less, although we had a huge registration, we have very less live. Probably because National Science Day, there are so many live online activities.
Yes.
So some may be catching up when the recorded later, when you can pause at will and so on. But still, we are going to give little bit gaps for. Yeah, Jishant is saying, please show each cell once so that he can
Okay.
quickly take a screenshot. Full cell
Yes.
once.
So this is the importing libraries part. This is loading data, and we'll share the this notebook in the WhatsApp group in the after the session. So don't worry if you are not able to like type in all the commands. Or this is opening the fits data. This is plotting. This is spinning of the light curve, and you can play around with this number to see what differences are coming. This is again plotting of bind data, and this is the fast Fourier transformation. So yes, you can take the screenshot of the full cell. And I hope you guys have typed in all the commands. So let's come to the fast Fourier transformation. And since you are typing this code, I'll once again explain what's doing what. So this is taking the fast Fourier transformation. And if you guys are not able to type all the commands, maybe what you can do is I'll just show you the main commands like which are needed. So actually, if you are not, if you're, you don't have to type these. You just plot with power only and remove all this if you, yes. So the only code you will have to see for the Fourier transformation is this, but now you won't be having this frequency on the x-axis. It's just the numbers, but this is the power density spectrum. Basically, these peaks are at particular frequency, and you can see the frequency from here. But we need frequencies. Right. So maybe you can type them.
Vishal, that's okay. We can wait for 5-10 minutes for them to type because frequency is an important information
Yes.
if they want to. So we can take a pause and allow them to write.
Yes.
So just to add, you can also create a discrete power density spectrum by writing your own code. But the power of fast Fourier transform is the algorithm by reducing the number of operations, and hence it makes the process speedy. So the number of operations required for the discrete power density spectrum is of the order of n square. But if you apply the fast Fourier transform algorithms, your number of operations reduced to n log n. So this basically, when you're dealing with the huge data sets, and that we do these days in astronomy, we try to follow those algorithms which can make the process faster. So this is the main advantage of using FFT over discrete Fourier transform or normal Fourier transform. But the the function is the same. It is converting your time into your frequency domain, and if there is an apparent signal in your time series, it will appear in the Fourier domain as a sharp peak. If it's a periodic signal in the form of sinusoid wave, it will be a sharp peak which will be appearing. And since these are the data which are from X-ray pulsars, you will be observing a sharp peak in the power density spectrum of these sources.
I think maybe now if we keep waiting for enough time for people to take screen captures, that would be sufficient perhaps if we are worried about overall time.
I believe everyone might have taken the screenshot by now, so we can move to the next section.
Uh-huh. Hmm.
Yeah.
Yes. Huh. Everyone
So
do that. Just keep taking
yeah,
screenshots of relevant bits.
yeah. Vishal, please rescale
Yes.
it on the x-axis so that they can
Yes,
see
yes.
the peaks.
So this is power versus frequency plot, and as you can see, there are peaks in the spectrum. That means some frequencies have higher power. That means some frequencies have higher contribution in the light curve. So right now, we can't see look at what frequency this peak is. So you can rescale your plot, and let's say I want to plot it in 0 to, let's say this 0.5. So what you can do is you can just exchange the x limits to 0 to 0.5, and you want to change the x ticks to, so you want 20 ticks in between 0.0 to 0.5. So let's run. So yes, so these three frequencies, you can see these have the higher contribution, and the lowest frequency is 0.130, around 0.130, and this is the periodicity which is present in this light curve, the light curve of 1626. So it has a periodicity of 0.130, and you are not getting a very sharp peak in this case. So usually the frequency contribution is so large that you get a very sharp peak and the power is very high. But since the time resolution of this data was 0.105, 0.125, which is just less than this periodicity, so you are not getting a very sharp peak. So if
Uh,
the time
yeah. So one contribution is from the time resolution of the light curve, and the other contribution is the shortness of the exposure time. To handle these light curves on Google Colab, we have actually truncated this to very short segments. So this is the another reason you are not seeing a significant peak. So Chetna mentioned when I talk about the significance of the peaks, which is basically the detection. I mean, how strong is your detection, or whether it's 5 sigma or beyond 5 sigma, which is a significant peak detection. Only because of the shortness of this light curve, we are unable to see a very sharp peak. But if you increase the exposure time with the same time resolution, because if you convert your frequency into period, which is 1 upon your frequency, which will give you the period, and for this particular source the period is 7.7 seconds. So even with the time resolution of 0.125 seconds, you will be able to have enough number of pulses collected. A number of pulses for of 7.7 seconds will be enough for have a detection of a period. But if you have a long light curve, then you will collect more data or more number of pulses, and hence a sharp peak. So this is the other reason why we are not seeing a very sharp peak in this light curve. This again depends upon the luminosity of the source also, because these are accretion rates. Different sources have different accretion rates based on the mass transfer rates from the companion star, because companion star is different in different objects or different binary systems. If your luminosity is higher of a particular system, in that case also you might see a strong peak in the same short exposure time. So it is very variable from system to system. This system has a moderate X-ray luminosity, like of the order of 10 is per 37 arcs per second, which if you compare with the Eddington luminosity discussed in the talk, is like 1/10 of that. So in order of magnitude less, and in that case, you are with this exposure time, the peak might not be that prominent. But if you take a source which is accreting at a Eddington luminosity with the same exposure time, and if the period of the system is of the same order, like let's say 7.7 seconds, you will still be able to see a sharp peak or a very significant peak in the power density spectrum. So this is our first example of playing with Fourier 1626. And Vishal, can you let them know which branch or which phase of the source it belongs to? Like there were different phases where spin flip happened. So which phase data is this?
I'm not sure about
Okay,
this.
so this is,
Yeah.
I believe, this is 1996 data, which is
Yes, this is
when the
this was
source was,
RxT data
yeah,
from 1996.
yeah. So this is when the source was spinning down. So in your exercises, you can convert this frequency into period and note down the period which you obtain with this power density spectrum. And similarly, when you play with the other light curve of the same source, Fourier 1626, which has already been shared on the Google Drive, taken on different branches, which is spin up after 2008 and before 1990, record the pulse period and see what is the change in fraction. I mean, it's on the decimal point you will find a change in the period. Not the 7 will not change to 8, but there will be change in the decimal number. So you can keep record of all those dates and also observe those light curves very rigorously by plotting or rebinning them, and see if you see changes in the intensity versus time plot also, because the light curve also changed from spin flip phases. So this is one exercise which you should all do when you submit your report. Now, Vishal, you can move on to the next source, maybe given the time
Yes,
constraint.
yes. So you can just change the file name. So the next source which I'll be showing is this. See, yes. So the next source is this Sen X3. So as you can see, the initial information, the basic to the first extension is primary, second one is rate, the exposure is 200 seconds, and the time resolution is 0.01. So in this case, we have higher time resolution than before. So you'll just need to change the file name, nothing else. You can just plot the light curve.
Oh, sorry, I was
So,
not. There were a couple of questions. Could we just take them before we move forward?
Yes, sure.
So, Rahul wanted to know about the usage of sigma. Maybe there are some students who have not yet encountered it. So, very quickly, if that could be said. And Anuva Banerjee asking, could you suggest how to obtain the detection significance of a peak in the PDS in terms of sigma? So, first, maybe just usage of sigma and then Anuvab's question.
Yes. So sigma is, yes, it's related to statistics. So sigma is basically the standard deviation from the mean point. So as you can see, the data points are like very fluctuating. So the if you take the average count per second over the whole time series, you'll get a value, let's say a mean. So you can see how much these data points, let's say these higher ones, are deviating from the mean. So that's sigma. And the second one is detection significance of a peak in the PDS. Maybe Aru can answer this question better.
So, detection significance in Python, you can have significance detection using different algorithms. So, basically, it's Monte Carlo simulations. It's beyond the scope of this workshop. So, we didn't want to go into those details. So, basically, you can simulate for large number of random sets. You can simulate these light curves for large number of times, let's say more than 10,000 times, and again creating the Fourier transform of each of those light curves 10,000 times and observing whether there is a chance probability that it is a false detection. So you calculate the false alarm probabilities of the detection of a signal in these light curves, and after calculating, if your false alarm probability comes out to be a very low number, then you say that this is a significant detection of a signal from the PDS. So this is something which is very time consuming, and it is also not something which you can do immediately. So that's why we didn't demonstrate to compute the significance of the signal in this workshop. But of course, if you're interested, you can take it further on your own, and we can help you out with the Monte Carlo simulations also, but that is beyond the scope of this workshop. So in that case, you compute the false alarm probabilities of a signal and then see how much significant the detection is. And there are different algorithms. There's not one way of calculating the significance, and it also depends upon the time series, type of time series you are dealing with. The method also has to be changed, and there are different sampling of data also. Like sometimes you get data with no data gaps, but at times you deal with light curves with uneven time gaps or time intervals, and in those cases your algorithm of dealing with those time series also changes. Okay, so these things are very dependent upon type of time series you are dealing with. And then you have more sophisticated tools than this power density spectrum, which is called sometimes called Lomskargel periodograms and so on. Again, not part of this workshop, which we have to undergo for dealing with such light curves.
Thanks. Please go ahead now, Vishal.
Yes, so as you can see, the time resolution of this light curve was 0.01 second, and you can't like reduce anything from this light curve. So this is all black because you are getting one data point in like 0.01 second. So in these cases, like this new bin is very helpful. So I'll just new bin into 2 seconds data, and then we'll try to plot it again. And now Hmm. You can see this. This is like two second worth of data is combined, and now you can see these peaks, and you can deduce something from this light curves, like variability or something, like if the some data points at some point of time are going very high or not. So let's see the fast this we'll go into frequency space and see the power density spectrum. And now you don't have to change anything in the code. Just you just have to change the file name so that the data is being read from the another file, and all the parameters are same. So you just need to run this block. So this is the power density spectrum of this source. So as you can see, there are these two frequencies contribution to this light curve, and as you can see, the power at these frequencies are like very high. So the average you can see like these peaks are having this 50,000 power, and these peaks are like more than 20. 1 second. 2 lakh 50,000. So these two frequencies like 0.210 and 0.421. So these are not two different peaks. So this is just the harmonic this. So this is the main peak, which the main frequency contribution, and this is the secondary peak which you get because of this peak. So this is the this I'm forgetting the word, sorry. So basically this light curve contains the periodicity of 1 divided by 210 second, 0.210, and which is uh, just a second, 210. So this light curve has a periodicity of around 4.5 seconds. So in the Fourier domain, we are getting this peak at this frequency 1 divided by 4.76. So this is the advantage of Fourier transformation. We are detecting the periodicities in the light curve using this tool. So from the light curve, it's very hard to see the periodicities. Like you can see these peaks, and these peaks are of 2 seconds or 4 seconds. So in the original light curve, we couldn't like deduce anything. So let's look at another source and see the light curve of that source if it's anything different from these.
So meanwhile, Vishal is typing in the name. So for you 1626, NAX3, LMCX4, these are different types of X-ray pulsar systems. So they are different types of objects which are having different types of companion star as well. So if you are interested in looking at the details of the companion star and understanding more about these sources, you can also go through the papers and links to these paper sources, which can give you more idea about the what is a companion star, and that has very much effect on the type of light curves and the periodicity you observe in these systems.
Yes. So this is another source, LMCX, and this is the main table looks like. So the exposure time is 18,240 seconds. So as you can see, the exposure time of this light curve is very large, and the time resolution is 0.1 seconds. So let's look at the light curve. So yes, so this light curve looks very different from the light curve which we have seen previously. So these light curves, like if you take the average count per second for this whole time series, it will be around not more than 50, let's say. And these peaks are around more than 600. So these are known as flarings in the light curve. So these arises due to various reasons. Sometimes it's because of detectors. So you can never be sure from the preliminary analysis that these are coming from the source itself. But in this case, these are coming from the source. So the source is, as you seen earlier. So these are binary systems. So sometimes these binaries, the neutron star, takes a large amount of mass, and due to this mass transfer difference, there can be flarings in the light curves. So you can zoom into the light curve and see the difference. So let's zoom into this portion. Zero. Yes, so you can see these are the flarings in the light curve, and let's bend this light curve to see much more clearly. So I'll again bend this light curve in 2 seconds, and again plot. Now you can see the flarings very clearly. So these are the flarings which are happening in the light curve. So you can further analyze these flarings, these light curve, and find out more about the source, like how the accretion is happening.
So this is an interesting source, LMCX4. And this is not in our own galaxy, as the name suggests. It is in LMC, in Magellanic clouds, large Magellanic cloud. And in this particular source, during these flares have been rigorously studied and was not observed throughout the orbit of the neutron star, which is of the order of 1.4 days. At intermittently at certain phases of the orbit of the neutron star, these flares were observed. And when these flares were studied in detail, the luminosity which was estimated from these flares was of the order of 10 to the power 39 ergs per second. So if you recall the Eddington luminosity value, which is of the order of 10 to the power 38 ergs per second, for a standard neutron star parameters like 1 solar mass and 10 kilometers neutron star radius, uh, this is these flares are super Eddington flares. So it means at this stage of a orbital phase of a neutron star, by orbital phase when the companion star and the neutron star were at a certain position, the mass accretion rate changed to super Eddington level, and hence these large flares were observed in the light curve. So this is one another type of variability which we observe in these kind of systems, apart from the periodicity. So if you can do the Fourier transform of these flares also, you will still see the period or the spin period of the neutron star.
Yes, so let's see the power density spectrum of the source. Yes, so as you can see, there are few peaks, but in the beginning, it's a very sharp peak you cannot see. So we'll have to zoom into this light curve. So first of all,
So
let's see in the full range. Yes.
so in the y-axis also, Vishal, the count rate or the power is of the order of 1 million. So that is
Yes.
another factor you have to rescale it.
So this is the full Fourier power density spectrum. So now we'll have to zoom into this later. So let's plot it in 0 to 0.1.
Vishal, you might want to zoom it on the y-axis also,
Yes,
and also
I'll,
you can play with the parameters in terms of plotting also. Like you can play with the log space and linear space. Then also you will see a different effect of that binning or the using different log or linear space. Sometimes you see a very sharp peak, which is more like a periodic signal. But if you want to understand the quasi periodicity in the time series, in the log scale, you might observe the broadening, which might not be very apparent if you observe the power density spectrum in the linear space. So those things you can play around in for yourself also. But these are the basic things. You can change the linear to log space.
so you can play around with this data more. So as you can see, there are peaks in this light curve. But
Vishal change the x limit to point 0.2, 0 to point 2.
so you'll have to change the x limit and y limit yourself and see what.
Now you can see the peak.
Yes. So you can see a peak at this 0.07 second hertz, and you can these are the peaks. These are the basically you can say the noise which is coming due to the flaring part, and these are
That
not
is due to
actually
the
noise.
time resolution. Time resolution
Time.
is showing up
It's
Yes.
in
not
the
always the time resolution effect. They can be also in when you study the power density spectrum, you can have different component of noises, which is sometimes called red noise, white noise.
White noise.
So red noise usually predominates at lower frequencies of your power density spectrum. So when you do this kind of periodicity search in your power density spectrum of Fourier domain, we might have to take care of these noise components also when dealing with such PDS. But for the current stage, we since we know these systems well and we know that there exists a peak around this particular this is the spin period of the neutron star, or for a known system, for working with any known system, if you know the spin period of the neutron star, you can, if you observe a strong peak or a strong signal at that particular frequency, you immediately say that this is a neutron star with the spin frequency, or you found a spin frequency in the power density spectrum. But if you're dealing with the unknown source, like there's a new source which is being discovered and there's no prior information about the source history, then you have to be very careful about these noise components which can dominate. There can be a white noise, which is kind of a random noise, which you have to subtract from your power density spectrum. And similarly, you have to take care of your red noise also in the power density spectrum. And by dealing with these noise components, then you find out which signal still predominates, is dominant in your Fourier transform. And then this is how you detect a signal in your Fourier transform or Fourier space. But then this is not the end, as somebody raised a question asking that detection significance. Then you have to run all those detection significance tests to understand whether there is a true signal in the time series, or there is any other false or the spurious event in the light curve that is causing that noise in the light curve, or that strong signal is not a true signal.
Yes.
And
Yes, since we have already studied this source, so we know that this is the peak, this is the periodicity in the system, so 0.07 second hertz. So this corresponds to the 13 seconds in the time domain. So this light curve, this LMCX4, contains a periodicity of around 13 seconds. So these are the tools which we use to probe into the Fourier space and find the frequency contribution in the particular light curve. So I've shown you three light curves. So in which this is was for flaring. So I'll hand over to Pinaki for some more sources. So, Pinaki.
Okay. So should I start now?
And
Uh,
I should, I have to switch the screen share, right? Okay, let me just add. Pinaki, your screen share is not in the studio yet.
Okay.
Meanwhile, while Pinaki is being added, I will flash one of the questions which was asked. Anubhav Banerjee, could we infer the underlying physical process triggering the band limited noise in PDS?
uh,
hmm. So one thing is periodicity, which is very apparent if it's a pulsar. So let me answer this question in a different way. If you are dealing with a unknown source or an unknown X-ray binary, and you first look at the light curve for any variability in the light curve, and then you go to the Fourier domain to look at this light curve and to see whether there is any existence of any periodicity if that is not apparent in your time series. If a periodicity is detected in the light curve, then it becomes very apparent that the compact object in that binary system is a neutron star, because it's a spinning neutron star and the spin frequency of the neutron star has been found, and it's not a black hole. So as compact objects can be of different types, and specifically when we talk about neutron star black hole binaries, and we wanted to understand what is the nature of the accretor in that binary system, one quick way to approach is to understand the nature of accretor is to study the power density spectrum and see whether there is any kind of variability apparent in your power density spectrum. If there is a clear signal at a spin frequency or at a sharp peak which can arise from the sinusoidal wave, that will give you a hint about the neutron star existence. But if you don't, if you observe a broad peak in the power density spectrum, which is also known as quasi-periodic oscillation of a particular frequency at a particular frequency, but there's a full width half maximum. Uh, there is a factor which is known as quality factor, which decides whether it's a QPO or not. If your quality factor, which is given by frequency over your full width half maximum of your feature, this ratio, if it comes out to be greater than 3, then you classify it as a quasi-periodic oscillation. Then you compare these features with all the known systems and see what is the characteristic of that frequency of that quasi-periodic oscillation. You look at the light curves at different times of, so you can have a transient basically. If you have an outburst in a particular source, then you look at the light curve at different phases of that outburst and see whether there is a evolution or at what phase of that So all this can be done in the power density spectrum, and from the Fourier transform, you observe these features or these variability features, and based on that, you can understand the what kind of features are these. This is first thing. But now coming to the physical processes, periodicity is clear. We know how the spin period or of the neutron star, how spin frequency is seen from the neutron star. Now question comes arise to the understanding the physical processes that it's causing quasi-periodic oscillations in the power density spectrum. Right now we do not have a very clear idea or clear image about what causes quasi-periodic oscillations in the system, but a vague idea or about is it's inhomogeneities in the accretion disk which is leading to that quasi-periodic oscillations. It can also be because of the beat between the accretion disk velocity, accretion disk velocity, and the spin period of the neutron star. Because of this, there can arise to a beat frequency that can lead to a particular frequency in your power density spectrum. So then you model these with different functions in the quasi power density spectrum, like you fit this power density spectrum with Lorentzian functions, because as we are not sure about the true physical origin of these features, it is believed it could be because of the damped harmonic oscillator. And to explain that damped harmonic oscillator kind of shape, you fit it with the Lorentzian. And when you fit these features with the Lorentzian, you can estimate the frequency, the exact frequency of these features in the power density spectrum. And based on that, you can uh, predict at what frequency and what is the quality factor and so on, and can get an idea about what could be the beat frequency of the neutron star. And if that frequency matches with the frequency which you have observed, then you can basically try to explain your observation with that beat frequency as the origin of that feature in the power density spectrum. So these are few ways, but again, there are different theories, and we try to model our quasi-periodic oscillations or different periodicity in the power density spectrum using that theoretical models. I hope you get some idea about how we try to figure out the physical processes in these systems.
Okay. Vishal, your screen share is now visible. Over to you. Oops. If you will go to your Google Colab notebook, then it would be.
Okay.
I'll add the screen share. Otherwise, it is showing picture in picture infinite. Yes.
Okay, can you see?
So yeah. Now your Google Colab is visible, and so you can go ahead, and you are audible.
Okay. So in the Vishal showed you LMC export layers.
Oh, there
So
is
now I will
there
show
is
different
there is a bit of a noise.
segment
Maybe
based
everyone
layers.
else mute.
So here I have loaded the LMC export extent light curve, which I shared with you earlier. So here you can see how the persistent emission of LMC export will be. So here are no such features of layers or any such else. So I hope everyone can see the light curve. So again, if I
Vish,
you can do the beginning.
Pinaki, there is a problem at your end with the internet, I guess.
Actually, we have lost him probably because of internet.
Yeah.
So
So,
he will be joining back, I think. Yeah, please go ahead.
Vishal, do you have the same screen? Maybe you can demonstrate the data.
Yeah, sure.
Yeah. So we'll be around only, so you can share your screen again.
Yeah, Pinaki is also back. Uh, and so right now, Pinaki, can you try screen share again? And if it
Yes, yes.
has continue to have problems, then we'll use Vishal's screen. But first, try yours.
No, it's okay.
Just go to the Google Colab. Yeah. And there is some kind of background noise. We will all mute
Okay.
our mics. Let's give it a try once again without noise if you are able to.
You can hear? Okay. Can you hear?
There was a bit of a noise, and also
Hello?
your screen share. I will
Hello?
add when you are on. You are not able to hear, perhaps. I will add your screen share once you are in the collab notebook. Yeah, I see that you are there. So let me just add your screen share. Yes. Oh, no. If you are in the studio, I'm not adding your
Okay.
screen share
You can
because
add.
it
You can
shows
add.
something.
You can
Yeah,
add.
yeah, yeah.
Okay.
So, and now we are
So
able to hear
everyone can
you, I
see
think, a
the
little
light
clear.
curve.
Yes.
Okay. So everyone can see the light curve of LMCX4. So this is the persistent emission of LMCX4. You can rebin it or you can as you wish, and you can then take the fast Fourier transform as showed earlier by Vishal and see that there is a sharp peak at 0.074 Hertz. And you may or may not get the harmonics of this peak. Next, I will show another segment of this source. So, okay, so I'm in the page.
In the meantime, I
So
would
I
like
will
to
load.
add, yeah, okay, if you are on. It is still loading. So I
Okay.
would like to add to what Aru said in reply to Anubhav's question that can we infer the underlying physical processes triggering the band limited noise. So I would like to tell you, Anubhav, that these periodic variabilities they arise due to the rotation induced motion of the accretion column, the accretion column through which the matter is flowing or getting funneled towards the magnetic poles. And if there is any instability in the emissivity, then that gives rise to the aperiodic variability. So, if the for the physical processes, if these inhomogeneities occur very far away from the surface of the neutron star, then we see the periodic and aperiodic variations independent of each other. But if for some reason the aperiodic variability, these inhomogeneities, they occur near the accretion column, then you will see these QPOs, they will be modulated. Their frequency will be modulated to the at the pulsar's spin frequency. So these can give an insight on the kind of variability and the inhomogeneities or the processes that are triggering the noise or the aperiodic or quasi-periodic variabilities. Yeah, okay, Pinaki.
Okay, so I hope everyone can see. So this is another segment of the LMC-X4 light curve. So you can see that there is a strong dip in the intensity. So this is due to the eclipse caused by the companion star in the binary of which LMC-X4 pulsar is part of. So you can see that there is a strong dip in the X-ray emission. It again it uh, reaches the persistent level, which have been showed earlier. So okay, so you can now experiment with these light curves. I will load another light curve. Say I will load Hercules X1. So this is an RXT observation. Okay. Okay. So I have loaded the RXT observation of Hercules X1. So here you can see the exposure of this light curve is around 3550 seconds and the time resolution is 0.125 seconds. So here is the light curve which shows this is the which has no such features as flares or something. So if it is too much detail, then you can rebin it and then have a look at the light curve. We will find if there is any signal in this light curve. So we will take the fast Fourier transform and see if there is any signal. Okay, so you can see a very strong peak at 0.808 hertz, which corresponds to about 1.24 second period time period of the pulsar spin period, which corresponds to the spin of the pulsar. So in fast Fourier transform, you have to remember that this power is not does not have any units. So this is the called the Fourier power, and this is and you can always normalize it by the length of the time series, which I have done here by dividing by n. Then you will get a power of say around 500 units. So here you can see how strong peak it is. So now I will show you another source. Uh, 36, let's say. Okay, so I have loaded the light curve of 4U1636. So the light curve is loaded. The exposure of this light curve is about 100 seconds and the time resolution is 0.5 seconds. Now we will see how the light curve looks. So you can see another feature which occurs in neutron star X-ray binaries, which is called an X-ray burst. So here you can see the burst, the the X-ray emission rising to very high level compared to the persistent emission, which is here. So the count rate is very high. So this is called a type 1 X-ray burst. And then you can do various studies of this X-ray bursts using some tools which are not shown here. For example, you can find the spin of the neutron star. You can find what are the spectral features of these X-ray bursts, etc. Sir, if you have you see duration is about 100. So now if you bin it like 10 seconds or 20 seconds, you won't see this feature
Pinaki, your voice is again
clearly.
breaking.
So you have to bin it of the proper order, 1 second or 0.5 second. Yes, ma'am.
So your voice was flickering. That's what I wanted to say. And just to add to Pinaki's point,
Okay,
he
so
mentioned that we can determine the frequency of the neutron star by doing the Fourier transform. But this spin frequency is way faster, or frequency is way higher compared to the previous sources which we did, like 7.7 seconds period system or 13.5 second system. Compared to that, the spin frequency of the system is extremely frequency is high. So we cannot do it with the light curve which we are going to provide you, but for that you need the default time resolution of the instrument to estimate the spin frequency of the neutron star, as that is very important factor to rebin and obtain the Fourier transform of the system.
since the this frequency emitted in this light curve is known to be very high, so also the resolution is of this light curve has to be very high to achieve that. I won't show the Fourier transform here. Or if you see the Fourier transform, you won't get any signal. So you will see that there is
Pinaki,
no
can you
such
tell them
peak in the
Pinaki,
Fourier transform. Yes.
can you tell them the frequency of the neutron star?
Yeah.
What is the spin frequency of the neutron?
Yes, the frequency of this
Okay, it seems we have lost him again due to poor internet.
Yes, yes, he's not there in the studio right now.
Yeah. So,
Can one of you take over with Vishal screen share is in the system right now in the studio.
Vishal, maybe you can take over that session, and if Pinaki joins, he can demonstrate if he wants.
Yeah, I've added Vishal screen share in. It's there.
Vishal, change the source name and just demonstrate the remaining sources.
Vishal, you are muted.
Uh,
Unmute.
Vishal, unmute yourself.
Sorry about that. So yeah. So which source was been uploaded?
Hercules X1.
Hercules. Yes. Yeah. So time note. So it's COL1 and COL2. Okay. Yeah, so exposure was 3550 and the time resolution was 0.125 seconds. And this is the light curve of the source. And Pinaki was showing you the FFT address with the default frequencies, I guess. So this is the full Fourier plot. This is power density spectrum of this source, and as you can see, these peaks, these sharp peaks in the light curve, and as you can see, there are very less noise in this light curve. So the frequency, the contribution we are getting is having a contribution is around 0.8. So let's have more ticks in this plot. Yes, so now you can see it's about 0.820. which corresponds to around 1.21 seconds. So this light curve has a periodicity of around 1.21 seconds, and the light curve is this. So let me bend the light curve in around 1 second. Yeah, so this is the light curve of the source, and as you can see these peaks, which corresponds to just 1.21 seconds, and you can always zoom in the light curve to see it more clearly. So let me zoom in around 50 to 70. So yes, so as you can see this, there are peaks in this light curve, which corresponds to 1.21 seconds, and the other source which Pinaki wanted to show you is. So this is another source for you 1636, and it's the light curve was taken in burst mode. So yes,
So,
the thought
Vishal, it is not the light curve taken in the burst mode. It is
burst.
a
I mean,
light curve. It is light curve of
yes,
an X-ray burst.
the X-ray
So
burst.
this is
Yes,
a different source. So if you remember the talk in the morning, we discussed about two types of neutron stars, one with strong magnetic field and other with low magnetic field. So this is a system which belongs to low magnetic field neutron stars. Until now, we were looking at the light curves of the sources which belong to X-ray pulsars. And this is a light curve of not an X-ray pulsar, but a bursting X-ray source, which is of having a neutron star with a magnetic field of the order of 10 is power 8 to 10 is power 9 Gauss. So, in this particular source, we observed X-ray transient, which is known as thermonuclear X-ray burst, and was discussed in the morning talk also that what are these bursts. So, we will see the profile in the real data of that thermonuclear X-ray burst with this light curve. And this light curve has been extracted with a bin size of 1 second to zoom in into that burst feature in the long light curve. So we have actually truncated this light curve. It's not like that light curve included only this burst. It was a long light curve, but again, as I mentioned, to handle the light curve in the Google Colab, we have to truncate it. So we just zoomed in into that feature of a thermonuclear X-ray burst in this light curve.
so what all sources were left with Pinaki?
I
I'm not
I
sure
think
if Pinaki showed this light curve.
Yes. Hercules
Pinaki, are you
X1
back?
also.
so. Her X1
Uh,
is already done. So I think after
yes.
that there are no more sources left. But as an exercise, all the participants should look at each of the light curves shared and plot them in the PDF and share it with us as a report. And as every light curve will have a different feature, so they should play with all the parameters given in the code and see if they can figure it out what are the changes in the light curves they observe in each case of the source, and also determine the periodicity in the case of pulsars and look at the light curve of thermonuclear X-ray burst with different bin sizes so that they can understand what is the importance of rebinning a light curve when you want to observe certain feature in the light curve. So I think, Ratnashri, with this, it should be end of the session for today. And if there are any,
Yeah. So if any of you have had any problem catching up, you could type here for any help that you need. And I think you know what we should give the participants time to actually give the reports that you are asking for, and
yeah,
maybe perhaps if it would. Of course, we continue in WhatsApp, and if there is a need felt, we come back for one more of such video interaction.
sure. Yeah, I mean, there is no rush to give submit your reports by today or tomorrow. Take a week's time, or if you need an extended time, WhatsApp us on the WhatsApp group
Yeah.
that you need an extended period because of several deadlines or anything else. Accordingly, we can I mean, extend the deadline. So there's no fixed deadline, but that will be good for us to know that you have learned something through this workshop.
Yes.
And in case
And
of any doubts, you can always ping us over WhatsApp.
Yeah,
yes.
Yes, we are there on WhatsApp, or if we need another session, we can try to arrange that.
yeah,
Uh, but
Yeah.
you should
Wa-
go through all these sources at least.
yeah, yeah,
Once at least some amount of work is submitted by everyone, then I think we could come back for one more kind of a wrap
yeah,
up session.
yes,
And
Yes.
also, I see that live actually very few have participated.
yes.
So I'm
That
hoping that in recorded segment, maybe more
more
others would come
viewers.
in. Today, of course, it is understandable because there seems to be so many online,
Yeah,
and
that is
it's typically the same group who have this keen interest, so they want to participate in everything. So
sure.
that I think we could wrap up the session here now. I don't see any questions which have come in now. So thanks everyone, and I am thinking that like if we do see sufficient amount of work output coming from the group, then maybe we could go in for one more session where some of the things which you said were at this time this is a simplified workshop. So some participants seem to be interested in doing a little more work,
Yeah,
So we
detailed
can
work.
go to the next
So we
step.
could
Yes, we
we
can go
could
to
go
the next step
maybe
if
as
there
a
is a lot of enthusiasm in this data analysis. I mean,
so
there is
thank
a lot
you.
more that can be achieved.
So thank you, Aruberi, Chetna Jain, Vishal Gaur, and Pinaki Roy. And
yeah,
thank you so much. And thank you all of you participants. And please do the work
sure.
so that you know, like this is not a lecture. What we did today was not a lecture. You have to submit your work.
Report.
Okay.
Thank you,
So
Ratashi.
and
Thank you
here,
for giving the opportunity to.
no thanks for helping us to
Thank you
organize this.
for this wonderful thing.
Yeah, thank you so
Thank you,
much.
We
Thank
Arun.
you, everyone.
continue.
Thank you,
Yeah,
everyone.
thank you.
So
Thank you, Vishal and